Hello, I'll be going over lessons 4.3 and 4.4 in this video. So starting off with lesson 4.3, the inverse of a matrix. So here are a few of the definitions. A square matrix is a matrix that has the same number of columns and rows. And the following matrices are examples of square matrices. And you can see an example for a 2 by 2, 3 by 3, and 4 by 4. The identity matrix for multiplication for all 2 by 2 square matrices is 1, 0, 0, 1. And an identity matrix called I has ones on its main diagonal and zeros elsewhere. The identity matrix for multiplication. Let A be a square matrix with n rows and n columns. Let I be a matrix with the same dimensions and with ones on the main diagonal and zeros elsewhere, like shown in the previous slide. Then A times I equals I times A, which results in A. And the product of a real number and 1 is the same number. The product of a square matrix A and I is the same matrix A. So you can see that when you multiply matrix A times I, you result in the original A. So what is the product of A, B, C, D, and 1, 0, 0, 1? The product of a real number and its multiplicative inverse is 1. The product of a square matrix and its inverse is the identity matrix I. So you can see that when you multiply A by the inverse of A, you result in the identity matrix I. The inverse of a matrix. Let A be a square matrix with n rows and n columns. If there is an n by n matrix B, such that A times B equals I and B times A equals I, then A and B are inverses of one another. The inverse of matrix A is denoted by A to the negative first power, and you have to note that this does not equal to 1 over A. In general, to show that matrices are inverses of one another, you need to show that the multiplication of the matrices is commutative and results in the identity matrix. And this is our first example. Let A equal 2, 3, 3, 5, and B equal 5, negative 3, negative 3, 2. And we need to show that A and B are inverses of one another. So we first are going to start off by multiplying A times B. And we're going to do this by using the first row of the first matrix and multiplying each by the first column of the second matrix. And you do the same thing for um, the second row in the first column, and also for the second row and the second column of the second one. And when you simplify, you should get 1, 0, 0, 1. And you're going to do the same thing for B times A. You're going to take the first row of the first matrix, multiply it by the first column of the second matrix, and you do the same steps for each of the other rows and columns, and you result in 1, 0, 0, 1. And since both product matrices are the 2 by 2 identity matrix for multiplication, A and B are inverses of one another. Each square matrix can be assigned a real number called the determinant of the matrix. Determinant of a 2 by 2 matrix is defined below. So let A equal ABCD. The determinant of A, denoted by DET, parentheses A, or ABCD, is defined as determinant of A equal ABCD equal AD minus BC. The matrix A has an inverse if and only if determinant of A does not equal 0. So find the determinant and tell whether each matrix has an inverse. So in problem A, G equals 7, 8, 6, 7, and we're going to find the determinant of G by using the expression shown in the previous slide, which was AD minus BC. And when we simplify that, we get 1, and since the determinant does not equal 0, matrix G does have an inverse. And for B, H equals 1, 1, 2, 2, we're going to use the same expression and we're going to simplify to get 0. And since the determinant of H is 0, matrix H does not have an inverse. Now our second lesson, lesson 4.4, solving systems with matrix equations. Refer to the system of equations at the right And for part A, write the system as a matrix equation. So we're going to first start off by writing the equations of the system in standard form with all the variables on one side. And then we're going to take the coefficients and separate them from the variables. And that will result in the right side of the equations. And then we're going to use that answer for part B, where we have to solve the matrix equation. And we're going to use the inverse of the first matrix and multiply it by the third matrix. And when we simplify, we get x, y, z equals -2 over 4 and 5. Thus, the solution is x equals -2, y equals 4, and z equals 5. Thank you.